David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 2301 statics. Got a couple of examples of moment by cross product. Remember that moment about a point is equal to R cross F. And this first example, we're going to demonstrate this rule. The position vector, you have some flexibility in what that is. You got to put the tail on the point that you're taking the moment about, but the tip can go on any convenient point on the line of action of the force. And if you're clever, and if you have the opportunity, you can shorten your calculations. So we'll show it by this example here on the two-dimensional example on the XY coordinate system. I have a vector F, which is 100 pounds. It's in the line of action, and I'm given 2 points along that line of action, A and B. Let's see where they are in the coordinates. And then I want to figure the moment about point C down here at 8, 3 coordinates. I want to find the moment about C and the shortest distance from C to the force F, or really also to that line. This also works for that. So I want to express my force in Cartesians, so I just take the coordinates of B, subtract from them the coordinates of A, and I get sort of a directed force vector, which is coordinates are 8 minus 0 in the I plus 7 minus 4 in the J. Divide that by the square root of sum of the squares. 8 squared plus 3 squared squared root is the square root of 73. So this force vector, force F expressed as Cartesian, is 93.6 I plus 35.1 J pounds. Okay, the easy way is because I can see the point C is directly below in the Y direction point B. I can get a real simple position vector, RBC, is equal to 0 I plus 4J. That makes my determinant, where I cross R with RBC with F, look like this: IJK 0, 4, 0. Remember, that's a position vector in the middle row. And 93.6, 35.1 is the force vector on the bottom row. The I's and the J's go to 0, and so I'm left with the K part, which is plus K times this little 2 by 2 vector, determinant. And I evaluate that. 0 times 35.1 is 0 minus 93.6 times 4. So that works out to be not negative 374 pound-feet in the K direction. The negative means I use my right hand rule and I point my thumb in the direction of the negative Z axis, which is the one coming out of the page in this example. So I point my thumb into the page and my fingers curl in the direction of the moment, which is this clockwise direction. So I get 374 pound-feet clockwise. Draw my little arrow there. Now I can do the same thing, should get the same number, using this more difficult position vector RAC, which is negative 8 being tip minus tail, 0 minus 8, negative 8, 4 minus 3, 1. This is my position vector. Put those into the same kind of determinant. Still got the force on the bottom, position vector here in the middle. Evaluate that. K times this little 2 by 2 is K times these numbers, negative 8 times 35.1 minus 1 times 93.6. Come up with the same negative 374 for the reasons I just explained. That's clockwise, 374 pound-feet. Same answer. Demonstrates this concept here. I can take my position vector to any convenient point. Finally, I want to find my perpendicular shortest distance DO from the vector, from that line to point C. That's just MO, the scalar, divided by F, the scalar. 374 divided by 100 is 3.74 feet. Okay, now let's do a more complicated 3D example. Z, X, and Y are my axes. I'm given that I have a force F, and I'm giving it to you in the Cartesian form. -10, 10, and 5. And my point of application of the force is A, and it's 0, 3, and 3 for the coordinates of it. I want to find the moment about the origin O first, and the shortest distance perpendicular from the vector to point O. Once again, it's R cross F. This time R is the position vector A over O. And here's my determinant, IJK, unit on the top, position in the middle. I can just write out my position vector, these coordinates, because they're everything minus 0, 0, 3, and 3. Put that in the middle. I've already got my force in the Cartesian format, so I just put that on this bottom row. I evaluate it out. Of course, this gets a lot more complicated. I got a lot more numbers to work with because I got an I times this little determinant, 3, 3, 10, 5, minus J times this determinant, everything except what's right under the J, 0 and 3, negative 10 and 5, put it over here. K is the same way, times this little determinant here, 0, 3, negative 10, 10. I've put it up here. I've written it out for you. This is how I recommend doing it on a test. When you're manipulating all these numbers and you're going to make an error, at least you have something to go back and check, see where you went wrong. Evaluating this first one, it's 3 times 5 minus 10 times 3, or 3 times 10. Evaluate these others this way. 0 times 5 minus 3 times negative 10. K is 0 times 10 minus 3 times negative 10. Carefully I evaluate all those. Works out to be negative 15I minus 30J plus 30K kilonewton meters. Now this means this force creates a negative 15 kilonewton meter moment about the x-axis. So I'd have to figure out what direction that is. It's really weird because it's in 3 dimensions. I point my thumb in the negative x direction, which is going away from me. You can see down here. My fingers would curl over like that. So my vector, my moment, is coming over the top, if you will, of the x-axis. I can evaluate the direction of these other 2 vectors by pointing my thumb in the negative y direction to get that one. So it's rotating that way over the y-axis away from me. And the z-axis, point my thumb positive up z, and it's wrapping around the z-axis coming at me from the left. That's where the right-hand rule really comes in handy on this 3-dimensional problems. I can get my scalar value of the moment about O, square root of the sum of the squares, 45 kilonewton meters. I can express F as a scalar, square root of the sum of the squares, 15 kilonewton, not meters. So my perpendicular distance DO is just the moment divided by the force, 45 divided by 15, 3 meters. Really hard to visualize, but kind of can see it maybe. Part B is find the moment about point B over here at -1, -3, 2, and the shortest distance. My moment calculation cross product looks like this. Put it in a determinant like this. The components of RAB, tip over tail, are 0 minus -1 is 1i, and so forth. 1, 6, and 1. Put that in the middle row of my determinant. My force is still the same, -10, 10, and 5. Evaluate it out like that. Very carefully. You can see it, follow it here. Works out to be 20i minus 15j plus 70k. It's probably useful for you to pause the video and do all this math on a piece of paper. Make sure that you've got to get good at evaluating these determinants, because there's going to be some of it in this class. Once again, I can get the square root of some of the squares to get the scalar value of MB, 74.3 kilonewton meters. F is still the same, 15 kilonewtons. Perpendicular distance, dB, is moment b divided by FB, the scalars, 4.96 meters. Real quick, a little review of the direction angles. Remember, the direction angles are the angles to the x, y, and z axis, alpha, beta, and gamma, and they are the cosine inverse of the unit vector that would apply to the moment vector MB. So it's just the I component, 20, divided by the scalar magnitude. Take the inverse cosine of that, I get 74.4 degrees. Do the same thing for beta and gamma, using -15 over 74.3 and then 70 over 74.3. Remember, it's important to keep that negative sign in there, because if I don't, I'm going to get the cosine of a negative number. Inverse cosine is going to be an angle bigger than 90, so it's important. It makes a big difference in what that direction angle is.